Our picture of the early universe was never wrong. It was incomplete. You were taught that the early universe was quiet, small, dim, almost empty. That story worked, because it was all our instruments allowed us to see. Then, in 2026, the James Webb Space Telescope looked farther back in time. What appeared wasn't strange because it existed. It was strange because something this massive existed too early in cosmic history. Tonight, you'll discover why the early universe wasn't small at all. It was already massive in scale, and now we finally have the evidence to prove it. Before we begin, if you find value in these deep space videos, a simple like or subscribe really helps this video reach more curious minds like you. Now, let everything soften, and together we drift into space. There's a difference between seeing something and being able to defend what you saw. Because the early universe is not just distant, it is fragile to our instruments, to our interpretations, to our own appetite for wonder. And for most of human history, far away was a feeling, a kind of cosmic poetry. But then we built a machine that refuses poetry unless it can be verified. NASA's James Webb Space Telescope didn't just give us prettier darkness. It gave us something colder and far more powerful. It gave us measured space, the kind of distance you can write down, argue over, test, and survive peer review with. And that is where this story truly begins. Because the early universe is not a place we can visit. It's a time we can only touch through photons, ancient light that has been travelling since before Earth had oceans. And the terrifying part is, light can lie, not intentionally, but because we are interpreting it through filters, through noise, through the imperfect lens of our own expectations. So if we're going to talk about something as heavy as the massive scale of the early universe, we need a rule, not a dramatic rule, a scientific one, a rule that keeps us honest. In astronomy, we can suspect a galaxy is very distant, a faint smudge, a dropout in certain filters, a shape that appears in infrared where it shouldn't. But suspicion isn't enough, because there's a cruel trick the universe plays on us. A closer object can sometimes imitate the colors of something unimaginably far away. Dust can redden light. Older stars can mimic a distant spectrum. Even a foreground contaminant, something sitting much closer, can hide inside the same pixel and corrupt the signal. This is why early universe claims live or die on contamination control and selection effects, the quiet, unglamorous discipline of not fooling ourselves. So here's the rule we live by. A distant galaxy counts as verified only when its distance is confirmed through spectroscopy, through the hard evidence of features in its spectrum, a break, a line, a signature that lands where physics says it must land. NASA describes it plainly. A spectrum spreads light into wavelength, letting us calculate redshift using identifiable features, evidence that can be checked, not just admired. And Webb is designed for this kind of truth. Its near-infrared spectrograph, NIRSpec, doesn't just take pictures. It takes the light and dissects it, measuring wavelengths across the infrared in modes built specifically to study faint, distant galaxies. This is why Webb's power is not just sensitivity, it's confirmation. It's the difference between saying, "We think we found something," and saying, "We can show you the evidence." Imagine this. You're standing in a dark room and someone slides a sheet of glass under a thin beam of light. On the far wall, the light spreads into a narrow rainbow, like a delicate ribbon. Now imagine that ribbon has missing slices, tiny gaps, like a barcode. Not random gaps, precise ones. Those gaps are where atoms stole specific colors of light. That barcode is identity, and if the entire barcode is shifted, stretched redder, longer, lower in energy, that shift is distance. Not distance like a road. Distance like time spent traveling while the universe expands beneath it. This is what spectroscopy gives us, a way to stop arguing about feelings and start arguing about physics. Here's the strange part. The earlier we look, the more the universe tries to sabotage certainty. Because we're chasing objects so faint that a small error doesn't just distort the result, it can invert reality. A tiny contamination becomes a false galaxy. A minor calibration problem becomes a headline. A seductive color becomes a phantom at the edge of time. Recent work on high redshift samples has emphasized how often foreground contaminants can slip into selections, especially when objects are barely resolved, and why careful verification matters. And NASA itself has been clear about the logic. Candidates can be identified photometrically. But the real milestone is when Webb spectra reveal the decisive features, like a Lyman break that locks in the redshift frontier. Scientists hate mysteries when the mystery is just bad data. So Webb doesn't just reach farther, it makes the early universe auditable. Now, we have to confront a word that sounds simple: scale. Most people hear massive scale and imagine size, a bigger galaxy, a larger explosion, a single monstrous object. But in cosmology, scale can mean something colder. How many? How often? How widespread? One spectacular galaxy can be a miracle. A population becomes a map. And this is where the way we observe changes everything. Some surveys go deep. They stare at a small patch of sky for a long time, letting faint galaxies emerge like fireflies in a fog. Other surveys go wide. They scan larger regions, catching rare objects and broader patterns, the statistical architecture of the universe. Reuters has described how Webb's observations, combined with careful survey strategy, help shape what we can say about the early universe, because the field you choose determines whether you're studying singular wonders or populations. A deep pointing can reveal faint galaxies we didn't know existed, but a deep pointing can also trick us, because if you stare at a tiny piece of sky, you might get lucky, or unlucky. You might find an unusually bright object and mistake it for the norm. That's cosmic variance, the uncomfortable truth that the universe is not uniform at small scales, and our sample can lie to us just by being small. Wide surveys fight that. Deep surveys reveal the faint truth, and Webb can do both, which means Webb doesn't just show us the early universe. It forces us to ask what kind of early universe we're actually measuring. Let's slow down for a moment and say the quiet part out loud. A photograph is not a distance measurement. A photograph is a hint, because light from a closer dusty galaxy can masquerade as a more distant pristine one in infrared colors, a known failure mode in photometric redshifts, especially in deep field data. But a spectrum is a courtroom witness. NASA's own explanation of distance measurement in astronomy centers on this. We infer redshift by identifying features in a spectrum and measuring how far they've shifted. And Webb's NIRSpec is built for exactly this kind of work, covering infrared wavelengths where the early universe's light has been stretched into visibility. This is why Webb keeps breaking records in a way that matters, not because it sees faint things, but because it can tell us what those faint things are. And if you could float out there, if you could stand in the darkness between galaxies and look with your own eyes, you would see almost nothing. Your vision isn't built for this. Our eyes are tuned to a narrow slice of reality, a tiny band of light that served us on Earth, under sun, under fire, under street lamp. But the universe doesn't care what our biology prefers. The earliest galaxies are often redshifted so deeply into infrared that our eyes would be blind to them. To human senses, the cosmic dawn would feel like silence. Webb is what happens when we admit our limitations and build an instrument that sees what we cannot. One more discipline matters here. Verification isn't only about one instrument shouting, "I saw it." It's about cross-checking. Images locate candidates. Spectra confirm them. Independent teams compare reductions. Features like the Lyman break are inspected for consistency, because a false break can emerge from noise if you're careless. NASA has highlighted this workflow in Webb Deep Field work. Images identify high redshift candidates, and spectroscopy then confirms them using decisive spectral features. And the wider scientific literature keeps returning to the same theme: interpret early universe signals carefully, build spectroscopic benchmarks, and don't confuse brightness with simplicity. This is the reality of cosmic archaeology. We are reconstructing a vanished world from a few stretched photons, and we only get one chance to be precise. So when we say the massive scale of the early universe, we are not going to mean it as a metaphor. We're going to measure it through 4 layers, 4 kinds of evidence that can be tested. Light, what exists, what's bright, what's numerous. Matter, how mass is distributed, even when it's invisible. Black holes, how early energy sources reshape their environments. Environments, how galaxies gather, cluster, and carve space itself, not as a prediction, not as hype, as a set of measurable doors we can walk through one by one, only when the evidence holds. Because this story is not about believing the universe, it's about confronting it. Einstein gave us the grammar of space-time. Hawking taught us that even black holes are not silent. But Webb is what happens when we aim that legacy at the edge of time and insist on proof. And now, with the rules set, with the instruments ready, we arrive at the most uncomfortable question of all. If we can verify galaxies near the beginning, and if we can count them, confirm them, and test them, what happens if the early universe wasn't a quiet dawn at all? What happens if it was already crowded, already loud, already organizing itself into structure, before we ever expected it had time? Because once far away becomes measured space, the edge stops being a rumor, and it becomes a number. There are moments in science when the universe doesn't feel like a place. It feels like a boundary, a cold line in the dark, where our instruments stop, where our certainty stops, where the story becomes rumor. And for decades, that boundary had a shape, a soft, fading edge, drawn by what our telescopes could almost see. But then NASA's James Webb Space Telescope pushed its hand through that edge, and the edge moved, not by a little, by a number we can defend. MOMSI 14, a galaxy with a spectroscopic redshift of 14.44, confirmed with Webb's near spec. That number doesn't sound like a place, it sounds like a code, but it is a timestamp. It means we are seeing this galaxy as it was around 280 million years after the Big Bang. And to feel what that means, we have to let our instincts fail for a second, because 280 million years sounds long, until we remember the universe is about 13.8 billion years old. This is not late history. This is the opening sentence. Back then, Earth didn't exist. The sun didn't exist. There were no oceans waiting to cool, no continents waiting to rise. MOMSI 14 was shining when our entire world was still impossible, and that should have been the end of the story, a record, a headline, a quiet victory. But then something was wrong. Distance alone is shocking, but brightness is what turns shock into a problem. Because MOMSI 14 is not just at the edge, it is remarkably luminous for where it sits in time, bright enough that it forces astronomers to stop thinking in terms of one lucky object and start thinking in terms of populations. Live Science described it in the language of disbelief. Webb breaks its own record again, yet the deeper punch is that this galaxy appears compact and intensely star-forming, producing far more light than many expectations for that era were comfortable with. The paper itself is blunt in a scientific way. It presents MOMSI 14 as a luminous source, ultraviolet absolute magnitude around -20.2, found in the cosmos field and confirmed by spectroscopy. Now, we can say -20.2 and move on. But numbers like that are supposed to do one thing in cosmology. They are supposed to tell us how rare something is, because the early universe is supposed to be a harsh place for galaxies. Everything is young, gas is still settling, heavy elements are scarce, and the background environment, filled with neutral hydrogen, makes it harder for certain light to escape cleanly. So when a galaxy this early shows up this bright, the quiet question becomes unavoidable. Is this a miracle? Or are we finally noticing a crowd we didn't know existed? Picture this. You're standing on a coastline at night, scanning the horizon for a single lighthouse. You expect one slow pulse of light. But then, far out in the darkness, you see something else. Not one beam, dozens, a whole line of lights, a city you didn't know was there. That's what bright early galaxies do to our expectations. One bright object can be an accident, but if bright objects are common enough to keep appearing, then the early universe wasn't a quiet shoreline, it was already lit. And that is why MOMSI 14 matters to scale, not because it is one far object, but because it anchors the bright end of cosmic dawn counts with spectroscopic confirmation, meaning it becomes a hard point in the census, not a hopeful candidate. The early universe is where mistakes become monsters, so the first thing we hold on to is the verification. The MOMSI 14 paper reports that Webb confirmed the redshift with near-spec prism spectroscopy through a sharp Lyman alpha break and detections of 5 rest ultraviolet emission lines, each one a piece of evidence that the redshift is not a guess. NASA reporting the result makes the same essential point. MOMSI 14 was spotted with near-cam and confirmed spectroscopically with near-spec, meaning this is not just a photometric whisper, it is a measured distance. This is the bedrock, because once the distance is confirmed, the universe loses its easiest escape route. It can't say, "You misidentified a closer imposter." It has to face the real question. If this light is truly from 280 million years after the beginning, what kind of physics is already happening that early? And this is where the story cracks open. Because the spectrum isn't only a distant stamp, it's a chemical confession. The paper reports strong ultraviolet emission features and points to nitrogen emission with an abundance pattern described as highly elevated, reported as supersolar nitrogen relative to carbon, with language that frames it as a striking enhancement. NASA highlights the same tension in plain terms. At only 280 million years after the Big Bang, there may not have been enough time for generations of stars to produce such high nitrogen in the usual way astronomers would expect. That doesn't mean the measurement is in doubt, it means the implications are uncomfortable. So NASA notes a theory raised by the researchers. The dense environment of the early universe may have produced supermassive stars capable of making more nitrogen than stars we see in the nearby cosmos. We hold that carefully, not as certainty, as a signpost. Because chemistry is not decoration. Chemistry is time. Every heavy element is a clock that says stars formed, lived, processed matter, and returned it, fast enough that Webb can detect the signature. And when nitrogen shows up like this, so early, it whispers something disturbing. Whatever was happening in the first few 100 million years was not gentle. Now, we have to be strict, because the early universe is a place where overconfidence turns into mythology. The paper is clear about what is solid and what is model-dependent. The redshift, the distance, is anchored in spectroscopic features. But detailed claims about masses, stellar ages, and star formation histories depend on modelling choices and assumptions, and the authors discuss those with the caution that real astronomy demands. That's not weakness, that's honesty. Because in this era of discovery, the temptation is always the same, to turn a measurement into a narrative too quickly. But MOMSI 14 doesn't need exaggeration. It already does something more unsettling than any headline. It forces us to separate what is measured from what is merely interpreted. And even the interpreted part is heavy. The paper describes MOMSI 14 as extremely compact, yet resolved, and argues this suggests an active galactic nucleus is not dominating the light, while also reporting very blue ultraviolet colour consistent with little dust and a young population. Again, measured features first, interpretation second. That's how the edge becomes real. And here is where MOMSI 14 stops being a record and becomes a pressure test for the whole field. The paper doesn't just present one galaxy, it connects MOMSI 14 to a wider surprise, a population of bright galaxies showing up at redshifts around 14 to 15 with a number density that the authors report as more than 100 times larger than pre-Webb consensus models. Now, those are words that can get abstract fast, so let's anchor them. Their survey coverage is reported as about 350 square arc minutes. That sounds like nothing, but in sky terms, it's a meaningful patch, roughly about half the apparent area of the full moon, half a moon's worth of sky. And inside that small slice, Webb is already pulling out galaxies from a time we once assumed would be nearly empty. This is why the word scale starts to change shape, because massive is no longer only about one galaxy's brightness. It becomes about the possibility that the early universe contained more luminous systems per cosmic volume than we expected, meaning the cosmic dawn may have been crowded with light earlier than our mental picture allowed. And this is exactly the kind of problem scientists secretly love, because it's not a mystery of fantasy, it's a mystery of numbers. And if you try to feel this, truly feel it, you run into a human limitation. Our minds want distance to be a road, so let's do it the honest way. MOMSI 14's light has been travelling for more than 13 billion years to reach us. That means when this galaxy was shining, there was no Earth watching, no human memory, no history. And yet the photons arrived anyway. They crossed an expanding universe and landed on a mirror built by human hands, then got split into a spectrum, measured line by line. So the uncomfortable truth is this: you are not looking at a distant place. You are looking at an era so early it barely deserves the word galaxy, and it is bright enough to challenge what we thought the dawn was allowed to look like. MOMSI 14 is a boundary marker, but it is also a warning, because once the edge moves out, it doesn't stay a single point. It becomes a frontier full of questions. If a galaxy this early can be this luminous, if the spectrum can already show chemical patterns that feel too soon, then the early universe is not just revealing objects, it is revealing systems, processes, growth. And that creates a deeper mystery, because light like this doesn't just appear. Something must power it, something must feed it. And in the shadows behind these early galaxies, Webb has been finding a strange population. Small, red, compact points that look like galaxies at first glance, but behave like something far more dangerous. Not stars, not normal galaxies, but the first young engines of gravity itself, black holes in their loudest infancy. And once we recognize that, the story changes again. For a while, the early universe felt almost understandable. We could point to a distant galaxy, measure its redshift, count its light, argue about how quickly stars formed. It was hard science, but it still sounded like astronomy we recognized. But then Webb started finding something that didn't behave like a galaxy should. Tiny, unreasonably bright, and red in a way that didn't feel like simple dust. They looked like little embers scattered across the deep fields, small red points hiding among the larger shapes. Astronomers began calling them what they looked like, little red dots. And at first, the name sounded harmless, but the longer we stared, the more disturbing the implication became, because these were not just objects, they were a pattern, and patterns in the early universe are never innocent. Here's the strange part: a normal bright galaxy has room to breathe. It spreads its starlight across space, billions of stars across thousands of light years, but little red dots pack enormous luminosity into something incredibly compact. So the old story offered two explanations, and both were uncomfortable. Either they were galaxies filled with absurd numbers of stars, or they were powered by something far more violent, a central engine, a black hole. Except, black holes are supposed to betray themselves. They should glow in X-rays. They should roar in radio. They should leave fingerprints that scream, accretion is happening here. But these objects were often quiet where they should have been loud. Weak X-ray and radio signals compared to their brightness. A mismatch that made the usual explanation feel unstable. So the mystery hardened. If these are black holes, why do they look so disguised? In January of 2026, a Nature paper put a sharper, colder frame around the problem. The argument wasn't vague, it was physical. It said, these little red dots are best explained as young supermassive black holes, not fully exposed quasars, not normal galaxies, but black holes still wrapped in something like a newborn shroud, a dense cocoon of ionized gas. That cocoon changes everything, because it doesn't just block light, it reprocesses light. It takes the raw radiation from the central engine and turns it into a spectrum dominated by nebular emission, glowing gas, making these objects look red, compact, and deceptively galaxy-like. In other words, they were not galaxies with weird colors. They were black holes wearing the light of their own fog. Picture this. You take a small flashlight, bright, harsh, undeniable. Now you put it inside a milk bottle. The flashlight doesn't stop shining, but the light is no longer sharp. It becomes soft, diffuse, milky. The bottle doesn't create the light, it reshapes it. That's what the cocoon is doing. The black hole is the flashlight, violent, concentrated energy. The cocoon is the milk bottle, ionized gas, and free electrons scattering, absorbing, and re-emitting the light until the object looks like a small red dot, not a screaming quasar. And once you accept that, the rest of the puzzle starts to line up. The nature work emphasized a crucial observational clue: broad hydrogen and helium lines, the kind of lines that, in many contexts, hint at high-velocity gas near a black hole. But here's where everything changes. The analysis argues the broadening can be explained largely by electron scattering in a dense ionized medium with a narrow intrinsic core underneath. That's not a poetic detail, it's a correction with teeth, because many earlier interpretations treated those broad lines as direct speedometers for gas orbiting close to a massive black hole. If the broadness is mostly scattering, then the black hole mass you infer from line widths can be wildly overestimated, and that leads to one of the most important turns in this whole story. For a while, little red dots were becoming famous for a terrifying reason. Black holes that seemed too massive too early, so overgrown that they threatened our ability to explain how they formed at all. But this cocoon model changes the scale of the monster. The nature analysis places upper limits on the black hole masses around 100,000 to 10 million solar masses, described as 2 orders of magnitude lower than some previous estimates. Live Science summarized the implication in plain language. Revised estimates suggest these black holes are around 100 times less massive than previously thought, easing the impossibly huge too early crisis. That doesn't make the early universe comfortable, it just changes the kind of discomfort, because now the picture is not unexplainable giants. It's something more subtle, and arguably more unsettling. A large population of young, lower mass black holes that are already shining hard enough to dominate what we see. Now, we have to speak carefully, because this is where science can get abused. We don't need to claim miracles. We only need to follow what the evidence allows. The Nature paper frames these objects as black holes accreting close to the Eddington limit, a known physical threshold where radiation pressure and gravity fight over the inflowing gas. That is already intense. It means these aren't quiet black holes. They're in a rapid growth phase, young engines consuming matter at a pace that pushes against the maximum steady brightness physics tolerates. And the cocoon makes that phase visible in a new way. Not as a naked quasar, but as a veiled one. And here's the part our instincts don't handle well. When we hear supermassive black hole, we imagine something the size of a solar system, something enormous in space. But what Webb is pointing us toward is not big in the way our eyes want. It's compact. So try to hold this in your mind. A source can pour out the light of a massive system, while the engine itself is confined to a region smaller than anything we can truly picture without losing scale. You could stare at one pixel in a Webb deep field and miss it, but inside that pixel, gravity is already building a future quasar, and the cocoon is the only reason we can see the process at all. Now we reach the point that connects this to the title of our journey, because massive scale isn't only about big galaxies, it's about systems appearing early. It's about the early universe not merely lighting up, but organizing itself into an infrastructure of energy sources. If little red dots were a one-off curiosity, we could treat them as an exception. But they're showing up as an emerging population in JWST surveys, enough to suggest this is a common phase, not a rare accident. That changes what early means. Because if rapid black hole growth was common, then black holes are not side characters in the cosmic dawn. They are part of the architecture. They are heating gas, ionizing environments, reshaping what galaxies become. And the cocoon idea helps explain something else that once felt like a contradiction. Why many of these objects could appear optically intense while remaining weak in X-ray and radio. The light is being processed, redirected, softened by the dense ionized shroud. It's not that the engine isn't there, it's that the engine is not yet exposed. This is the uncomfortable truth. For a moment, we were cataloguing pieces of the early universe as galaxies, while some of them may have been black holes in a formative stage, a brief era where a growing supermassive black hole is wrapped in ionized gas, shining through a veil like a lantern inside fog. That doesn't diminish the beauty, it deepens it, because it means the cosmic dawn wasn't only about stars igniting, it was also about gravity igniting. And when gravity ignites, it changes everything downstream. But then, the universe offers a sharper test, because little red dots are a population, and populations are powerful, but they can feel abstract. So the next step is inevitable. We look for a single object where Webb spectroscopy doesn't just imply a hidden engine, it shows it with more direct, unmistakable spectral fingerprints. A specific early galaxy, already famous, already studied, that suddenly reveals something like teeth in its spectrum. A sign that the black hole story isn't only hiding in tiny red points, it's embedded inside one of the brightest early galaxies we know. Its name is GNZ11. There is a special kind of silence in deep space, the kind that makes us believe the early universe must have been quiet. But GNZ11 refuses that comfort, because GNZ11 is not just a distant galaxy, it is one of the most luminous galaxies ever found at extreme redshift, a bright blue beacon from a time when the universe was still learning how to make structure, and when Webb finally took GNZ11 seriously, not as a faint smudge, but as a spectrum worth dissecting line by line, the galaxy didn't just shine, it confessed. In Nature, Roberto Maiolino and collaborators presented a deep JWST near-spec analysis of GNZ11 at redshift 10.6, and they reported spectral features that are typical of an active galactic nucleus, evidence that GNZ11 hosts an accreting black hole. Not a rumour, not a photometric suggestion, a spectral diagnosis. And this is where the story becomes uncomfortable, because this time, the black hole isn't hiding inside a tiny red dot. It's embedded inside one of the early universe's most luminous galaxies. Little red dots taught us something unsettling. In the cosmic dawn, black holes can wear disguises, but GNZ11 matters differently. Because GNZ11 is not subtle, it is exceptionally bright for its era, already famous long before Webb. and Webb's near-spec data are deep enough that the argument doesn't rest on a single ambiguous feature. This isn't the story of a hidden ember. This is the story of a galaxy with a blade inside it, and the evidence comes from the kind of fingerprints astronomers learn to fear and respect. In that nature analysis, Webb's spectrum of GNZ11 shows transitions such as NE4 at wavelength 2423 and C2 star at wavelength 1335, features described as typical of active galactic nuclei. Then it gets stranger. They also report semi-forbidden nebular lines tracing gas, densities higher than 1 billion particles per cubic centimetre, densities that are typical of the broad line region of active galactic nuclei. Now, we have to translate what that means without turning it into a lecture, because gas density can sound harmless, but densities like this do not belong to normal galaxy-wide nebulae. They belong to environments pushed to extremes, gas forced into tight spaces, heated, ionized, compressed, close enough to a central engine that the physics starts acting sharp. This is why the paper's conclusion is so heavy. These spectral features indicate that GNZ11 hosts an accreting black hole. We are not guessing a black hole exists. We are reading the environment that black holes create. Picture this. You walk down a hallway at night. Everything is dark and quiet. But under one door, light is leaking out. Thin, bright, unnatural. You don't have to see the furnace to know it's there, because the air is warmer near that door. The paint looks stressed. The light has a harshness that doesn't belong to a lamp. That's what these spectral lines are. We don't see the black hole directly. We see what it does to the gas around it, how it ionizes, excites, and reshapes matter until the spectrum starts behaving like a warning sign. Now, we have to be disciplined with language. It is tempting to say, the black hole dominates GNZ11, but dominance is a strong word. So we stay inside what is measurable. The nature work frames the evidence as AGN-like spectral components, grounded in identified transitions and line diagnostics, NE4, C2 star, and extremely high-density gas tracers, consistent with an active nucleus. That is the fact-safe core. An active nucleus is present. Accretion is the consistent interpretation. And the argument is built on spectral fingerprints, not vibes. At the same time, the broader literature around GNZ11 has discussed how hard it is to separate starburst signatures from AGN signatures at these redshifts, and how some lines, like nitrogen features, can complicate the story rather than simplify it. That doesn't weaken the result. It reveals what makes GNZ11 such a powerful test case. It forces us to hold two truths at once: a luminous early galaxy and evidence for a central accreting black hole, in a universe that supposedly hadn't had time to build either comfortably. GNZ11 is seen at a time roughly a few hundred million years after the Big Bang, around 430 million years in the JWST spectroscopy work that refined its redshift to 10.603. To feel that timescale, we have to say the quiet truth. Back then, Earth didn't exist. The Sun didn't exist. There were no continents, no oceans, no biology. The universe was young enough to still be dangerous, and yet here is a galaxy already luminous, and inside it, a black hole already feeding. Einstein gave us the idea that gravity is geometry. Hawking showed us that black holes are not simple, not silent. But Webb is doing something else. It is showing us black holes not as end states, but as early infrastructure. And if you were out there, floating near GNZ11, you wouldn't see a dramatic monster. You wouldn't see a swirling black disk the way Hollywood imagines it. You would see nothing. Not because nothing is happening, but because your eyes are not built for this era of light. The signatures are buried in infrared wavelengths and in subtle spectral ratios, in the way specific lines appear, shift, and sharpen. This is why Webb matters. It doesn't just show us a picture. It turns the early universe into a readable document, a document written in lines, breaks, and densities. Now we arrive at the question everyone wants answered too fast. How did a black hole show up this early? This is where we must not exaggerate. The fact-safe statement is simple. Early, accreting black holes exist. Webb is finding evidence for them in multiple forms, little red dots, and now GNZ11 with strong AGN like line diagnostics. But explaining their seed origins, how the first black holes formed and grew into these early engines, remains an open modelling problem. That's not a gap in knowledge to be embarrassed by. It's a frontier. Scientists can propose pathways, test them, discard them, refine them, but the documentary stays anchored to what Webb actually measured: a luminous galaxy at redshift 10.6, a spectrum with AGN typical features. Dense gas conditions consistent with a black hole's immediate environment. Here is the deeper reason this matters to the massive scale story. If GNZ11 were just a galaxy, it would already be impressive. But GNZ11 is a galaxy plus an engine. That changes what scale means, because the early universe is not only assembling stars, it is assembling power, sources, objects that can flood their surroundings with ionizing radiation, drive outflows, and reshape how gas behaves. This is the infrastructure of the cosmic dawn, not roads and buildings, but gravity wells and radiation fields. Not cities made of steel, but cities made of plasma, starlight, and accretion. And when we find evidence that these engines are present inside exceptionally luminous early galaxies, we're forced to accept something quietly staggering. Black holes are not side characters. They are woven into the early universe's main plot, part of how the first large systems light up, heat up, and transform the space around them. But then the universe gives us one more twist. Because a black hole doesn't just sit inside a galaxy, it interacts with its environment. It changes the transparency of the surrounding space. It changes which photons escape and which get swallowed by hydrogen fog. And GNZ11 has been discussed not only as an AGN hosting galaxy, but as an object with signs of a larger scale environment, an extended Lyman alpha halo reported in follow-up work using Webb's integral field spectroscopy. That raises a new, sharper question. If we can see light like Lyman alpha leaking out this early, through a universe that should still be thick with neutral hydrogen, then the early cosmos isn't just producing bright objects. It's producing pockets of transparency, local regions where light punches through the fog. And that is where the next part of our journey tightens. Because the next mystery is not a galaxy. It is the space between galaxies. The hydrogen itself, the ancient barrier that decides whether the early universe stays dark or starts to open. There's a moment in every cosmic story where the enemy isn't distance. It's the medium, not the galaxy, not the telescope, but the space between. Because the early universe wasn't simply dark, it was fogged. For a long stretch of cosmic time, space was filled with neutral hydrogen. Atoms with a quiet, brutal talent. They don't have to destroy light to stop it. They only have to scatter it, again and again, until a clean signal turns into nothing but haze. And one photon in particular suffers more than almost any other. Lyman alpha, a specific shade of ultraviolet light produced when hydrogen changes state, one of the most common fingerprints of young star-forming galaxies, and one of the easiest for neutral hydrogen to erase. So for years, the expectation was simple. If we go early enough, deep into the cosmic dawn, Lyman alpha should vanish. Not because galaxies aren't shining, but because the universe is still wrapped in a hydrogen barrier that won't let that light travel straight. That expectation was a kind of compass. It helped astronomers map the timeline of reionization, the era when the first luminous objects gradually ionized the surrounding hydrogen turning fog into clarity. But then Webb found something that shouldn't be easy to find. Not a hint, not a maybe, a line, a clean, bright signature punching through the fog at redshift 13. And that is where the universe stops feeling patient. Let's slow down and make the physics feel real. Neutral hydrogen is everywhere in the early universe, and Lyman alpha interacts with it almost perfectly. So, when a Lyman alpha photon leaves a young galaxy, it doesn't travel like a bullet. It travels like a person trying to cross a packed crowd, bumped, redirected, turned around and delayed until it no longer points back to where it began. On cosmic scales, that means the photon effectively disappears from our line of sight. This is why transparency is not a poetic word. Here, it's measurable. It's the difference between the universe lets this wavelength travel and the universe does not. And this is why Lyman alpha at extreme redshift is so provocative, because it suggests, at least locally, someone turned on a light inside the fog. Webb's JADES program obtained spectroscopy of a galaxy at redshift 13.0 and reported a singular, bright emission line unambiguously identified as Lyman alpha, along with a smooth turnover in the ultraviolet continuum associated with absorption near Lyman alpha. This is not a photometric guess. It is spectroscopy, a measured feature placed where physics says it must be when the universe has stretched the light that far. And the time this represents is not abstract. The NASA material describing this object places it at about 330 million years after the Big Bang. 330 million years, and yet here is hydrogen light, still intact enough to be measured. Picture this. You're outside on a cold night. Fog so thick you can taste it. You shine a flashlight. Up close it looks bright. But 10 steps out, the beam collapses. The fog doesn't kill the light. It just scatters it until it can't form a clean path. Now imagine you suddenly see a sharp beam cutting through anyway. What would that mean? It would mean the fog isn't uniform. It would mean there are pockets, local clearings where light can travel. That's the feeling of this detection. Not the whole sky is clear, but somewhere a hole opened. This is where we have to be disciplined, because a result like this tempts people to overclaim. A Lyman alpha detection at redshift 13 does not mean the entire universe was already reionized. It means something narrower and more interesting. At least some regions allowed Lyman alpha transmission earlier than many expectations, consistent with patchiness, clarity forming in islands, not all at once. The Nature paper frames the Lyman alpha equivalent width as greater than 40 angstroms in the rest frame, noting that values like this were previously only seen at lower redshifts where the intergalactic medium is increasingly ionized. That's a controlled way of saying something unsettling. This line looks like it came through an environment that behaves more ionized than we expect at that time, and the authors connect it with other clues in the spectrum, like an extremely blue ultraviolet continuum, arguing it indicates a galaxy that produces and leaks ionizing photons effectively enough to carve out an early ionized region around it. But even that is handled carefully, because the next word, bubble, has to be used like a scalpel. The concept is simple enough to visualize. If a young galaxy produces enough high energy, ultraviolet light, it can ionize the hydrogen around it. That creates a local region where Lyman alpha has a better chance of escaping without being scattered into oblivion. A bubble. But the size of that bubble, how far it extends, how quickly it formed, what fraction of the surrounding hydrogen remains neutral, depends on models, assumptions, and uncertain inputs. So we state it precisely. The Lyman alpha detection is consistent with a local ionized region around the galaxy, but the bubble's size and the broader ionization state remain model-dependent. This is the correct kind of uncertainty, not vague, not evasive. It's the honest boundary between measurement and interpretation. Here's where the discomfort deepens. because even a small amount of neutral hydrogen can strongly affect Lyman alpha. This is why Lyman alpha has been used as a reionization probe in the first place. So if we see a clear Lyman alpha line at redshift 13, we're forced into a more complex picture of the early cosmos. Not a smooth timeline, not a single switch flipping from neutral to ionized, but an uneven landscape. Some regions still opaque, some already pierced. A universe where early galaxies are not just passive lights in the dark, but active agents reshaping their surroundings. And that means the early universe had environmental structure much earlier than our instincts want to grant it. And this is the moment to place you inside the science. Because when you imagine looking back in time, it feels like watching a recording, as if the universe is simply offering us its past. But it isn't. The early universe resists being seen. It hides behind neutral hydrogen. It scrambles the most useful lines. It turns clean evidence into fog. So when you hear, "they detected Lyman alpha," don't hear it as trivia. Hear it as a breach, a single wavelength, escaping a time that was designed to trap it. NASA's own spectrum graphic for JWST 13-1 emphasizes the same core shock. Bright Lyman alpha emission from a galaxy at roughly 330 million years after the Big Bang, despite the expectation that such emission should be strongly suppressed by neutral hydrogen. Now, we tie it back to the title we're living inside. Massive scale is not only about the brightness of distant galaxies, it's about the scale of space itself becoming an actor. Reionization is an environmental transformation across enormous volumes, the space between galaxies changing phase, gradually, unevenly, driven by early sources of ultraviolet radiation. That means galaxies and black holes don't just exist in the universe. They help decide what the universe is like, how transparent it becomes, how radiation travels, how the cosmic web heats and evolves. And once Lyman alpha begins to leak out at redshift 13, even locally, the story stops being only about objects. It becomes about regions, about bubbles and boundaries, about how the first lights didn't merely shine, they cleared paths. So the calm, fact-safe conclusion is not dramatic, it's sharper than drama. Webb and Jades detected unambiguous Lyman alpha at redshift 13, which implies that at least some regions allowed transmission unexpectedly early, consistent with local ionized zones, without claiming the entire universe was already reionized. A fog that thins in patches, a universe that opens unevenly, and a deeper implication that refuses to leave us alone. If light can punch through this early, what else is already forming behind the fog, quietly, chemically, irreversibly, marking the first galaxies not just with brightness, but with the earliest fingerprints of processed matter? There's a reason astronomers don't treat chemistry like decoration. In the early universe, chemistry is a verdict, because the first few 100 million years after the Big Bang were supposed to be simple, almost brutally simple. Hydrogen, helium, a trace of lithium, a cosmic newborn room barely furnished. And when we look that far back, we want to believe we're seeing purity. But the universe is rarely pure, and Webb has been teaching us that the cosmic dawn wasn't just about light appearing, it was about processing, matter being cooked, torn apart, rebuilt, and marked. Not with poetry, with lines, with wavelengths that land where they must land, because element lines are not vibes. They are wavelength-locked evidence. If oxygen is there, the spectrum doesn't whisper it, it pins it to the wall. When we talk about chemical enrichment, it's easy for it to sound like interpretation, like a story. But the science is colder than that. Atoms emit and absorb specific wavelengths, like a signature carved into the rules of physics. When the universe stretches that light across billions of years, those signatures shift, but they stay intact enough to be recognized. That's why spectroscopy is so unforgiving. It doesn't ask what we hoped the early universe would be. It tells us what it was. And in JWST 14-0, the evidence arrived from an unexpected partner. Not Webb alone, but Webb and ALMA. JWST 14-0 was first identified with Webb as an extreme distance galaxy candidate, with Webb's near spec estimating a redshift around 14.3, less than 300 million years after the Big Bang. Then ALMA followed up, and in 2025 ALMA announced the detection of oxygen in JWST 14-0, described as the most distant detection of oxygen, and a sign the galaxy was more chemically mature than expected that early. The peer-reviewed analysis behind that announcement is even more precise. It reports a robust detection of the O3 line at 88 microns, giving a spectroscopic redshift of 14.1793, and tightening the distance measurement dramatically compared to the earlier near-spec estimate. So now we're not talking about maybe, we're talking about a line detected at high significance, a distance pinned down to a razor-thin uncertainty, and oxygen, real oxygen, present in a galaxy seen when the universe was still in its first breath. That's when the story stops being about how far we can see, and becomes about how fast the universe learned to evolve. Picture this. You walk into a house that was built yesterday. The paint is still drying, the air still smells like fresh wood, and then you see something that makes your stomach drop. Rust. Not a little stain. Real oxidation. Evidence that metal has been exposed, processed, aged, long enough for chemistry to leave a scar. You don't need a theory to feel the contradiction. Rust means time and processing. Oxygen in the early universe is like that. It doesn't mean the galaxy is old in human terms, but it means stars lived fast enough and died hard enough to manufacture heavy elements and spread them into the galaxy's gas, early enough for our instruments to catch the signature. This is where we have to stay honest. Oxygen detected does not mean mature like the Milky Way. It does not mean calm, spiral arms and settled, long-lived star populations. It means something simpler and more intense. Stars formed quickly. They processed primordial gas. They returned material back into the galaxy. Enough oxygen existed in the interstellar medium to produce a detectable line. That is already staggering. Because the early universe was supposed to be a place where galaxies were still learning how to be galaxies. And yet, here we are, reading chemical fingerprints that imply rapid cycles of birth and death. This is where the story tightens. MOMZ14 at redshift 14.44 shocked us with distance, and with spectral signs pointing to unusually strong nitrogen features, described in the paper as highly supersolar nitrogen to carbon. JWST 14-0 shocks us with oxygen, confirmed through ALMA spectroscopy at redshift 14.1793. We do not need to claim these two galaxies share the same detailed history. We don't need to overconnect them. The safe connection is more powerful than any speculation. Across multiple extreme redshift systems, Webb-era astronomy is seeing chemical complexity appear early. Different elements, different diagnostics, same quiet implication. The cosmic dawn was already running fast. Here's the uncomfortable part. Oxygen is not primordial. Oxygen is manufactured inside stars. So oxygen this early means the universe didn't waste time. It means star formation began, intensified, and cycled material rapidly, fast enough that by the time the universe was under 300 million years old, the gas was already marked. And the detection doesn't just tell us oxygen exists, it also improves the precision of the galaxy's distance measurement, because the oxygen line gives a clean spectroscopic anchor. That matters because the early universe story lives and dies on what we can defend. If we're going to claim the dawn was crowded, if we're going to talk about massive scale, we need hard anchors. Oxygen is one of them, and this is the moment to slow down and place you inside the reality. When you hear oxygen in the early universe, your mind wants to turn it into trivia. But oxygen is the element you breathe. It's in your blood, in the oceans, in the rust on old iron, in the stone beneath every city. And Webb and ALMA are telling us that the raw ingredients of a future like ours were already being forged when the universe was still an infant, long before Earth, long before the Sun. You're not just watching a distant galaxy, you're watching chemistry begin to take the universe personally. One oxygen detection could be a curiosity, but paired with MOMSI 14's chemical strangeness and the growing list of bright confirmed galaxies at extreme redshift, it becomes a different kind of statement. Not one galaxy got lucky, but early star formation and enrichment may have been widespread enough that we can catch it repeatedly, even at the edge. This is what massive scale starts to mean in a measurable way, not size as a metaphor, but the scale of processes, star formation, enrichment, radiation, already operating across multiple systems, across volumes of space that are large enough to matter. So the calm conclusion is not dramatic, it is heavier than drama. By less than 300 million years after the Big Bang, we have a galaxy whose oxygen line can be detected and used to measure its distance with extraordinary precision. That means the early universe wasn't only igniting, it was already transforming. And once chemistry appears this early, a deeper question replaces the one we just answered. If galaxies were already enriched, already complex, already fast, what were they building on? What invisible structure was holding them, guiding them, shaping where this early chemistry could gather, before the light ever made it obvious? There's a certain illusion we live with. We look up and we think the universe is made of what we can see. Stars, galaxies, light. But that is not the real architecture. Most of the universe's matter does not glow. It does not shimmer. It does not announce itself. It holds everything together, while remaining invisible. And for most of human history, that invisibility felt like a wall. Because how do you map something that refuses to emit light? How do you prove a structure you cannot photograph? But then, quietly, astronomy learned a different language. Not the language of brightness, the language of distortion. Because gravity doesn't need permission from light. Gravity bends whatever passes through it. And in January 2026, NASA and JPL released something that feels almost like a violation of the old rules. A Webb image containing nearly 800,000 galaxies overlaid with a dark matter map, blue density drawn from gravitational lensing, not from light, not a simulation, not an artist's impression, a reconstruction pulled from the way mass quietly warps the universe. And the moment we see it, we realize something cold. We have been staring at the decorations of the cosmos, while the true structure was always underneath. Dark matter doesn't glow, so Webb can't see it the way it sees a galaxy. Instead, the team used gravitational lensing, the way mass bends space-time, and space-time bends the paths of light. When light from distant galaxies travels toward us, it passes through a foreground landscape of mass. That mass, mostly dark matter, acts like an uneven lens. Some galaxy images stretch slightly, some shear, some tilt just a little, like reflections in imperfect glass. The distortions are tiny, almost insulting to our senses. But when you measure them across huge numbers of background galaxies, the pattern becomes readable. Reuters described it simply: the Webb map leveraged the way dark matter distorts the light. From roughly 250,000 distant galaxies across a patch of sky nearly 3 times the size of the full moon, creating what they called the most detailed dark matter map yet in that region. That scale matters because dark matter is not an object. It's a field. It clumps, stretches, forms halos, bridges, filaments. It makes a geography. And we can only read that geography by using the universe's own lensing as our instrument. Picture this. You're standing in a field. You can't see the wind, but you can see what it does. The grass leans. Ripples travel in waves. A pattern sweeps across the ground, revealing a force with no visible body. That's what weak lensing is. Dark matter is the wind. Galaxies are the grass. We don't see the wind. We watch the grass bend, and we reconstruct the invisible motion. This is why lensing is so powerful and so unsettling, because it means the universe carries its own evidence. Even when the culprit is invisible, the victims remember. This new web-based map isn't just another dark matter map. NASA and JPL emphasize the leap in detail. The JPL release quotes lead author Diana Scognamiglio describing it as the largest web dark matter map they've made, and twice as sharp as any dark matter map made by other observatories. That twice as sharp isn't a brag. It's an increase in usable information. Because lensing maps live and die on how many background galaxies you can measure, how many clean shapes you can trust. Webb's resolution and infrared sensitivity mean it can see more faint galaxies, farther away, with shapes that are still measurable. Reuters linked that improvement to the map's higher resolution compared to earlier Hubble-based maps. In simple human terms, if earlier maps were like trying to understand a coastline through fog, this is a day when the fog thins and the cliffs finally have edges. When people say cosmic web, it can sound like metaphor, but lensing maps make it literal. The NASA release describes dense regions of dark matter connected by lower density filaments, forming a web-like structure, with ordinary matter tending to trace that same underlying pattern. That's what threads means in a fact-safe way, not poetic strings in space, a reconstructed mass distribution where higher density regions connect through lower density bridges, filaments that guide where galaxies form and cluster. Reuters described how the new map enables detection of finer dark matter structures and more precise visualization of the cosmic web, this network of clusters and filaments. And suddenly, the early universe stops looking like a random scatter of lights. It starts looking like a system with a skeleton. Here is the quiet principle that changes everything. Galaxies do not begin the story. Mass concentrations do. Before the first stars ignite, gravity is already at work, pulling matter into denser regions, deepening potential wells, shaping where gas will later fall, cool, and light up. A P framed it in a way that cuts through the romance. Dark matter forms an invisible framework connecting galaxy clusters, and mapping it helps explain how the universe grew its large-scale structure. That's the reason this belongs in our journey. Because if we are trying to understand massive scale, we cannot stop at bright galaxies. Brightness is the symptom. The underlying cause is where the mass lives, and this is where we have to admit something about ourselves. Your eyes are brilliant at survival. They are not brilliant at truth. Your eyes evolved to catch movement in a forest, to find faces, to judge distance across a few hundred meters. But dark matter does not present itself as a visible object. It presents itself as a statistical pattern, a collective distortion of hundreds of thousands of galaxies. So if you were floating out there, inside that web field, you would not see the scaffolding. You would see galaxies. You would miss the force that arranged them. And that is the disturbing beauty of what Webb has done. It doesn't just extend our vision, it replaces our instincts with measurement. Now, let's make the scale feel physical. NASA's image description says the field contains nearly 800,000 galaxies, and the overlay shows darker and brighter blues, indicating lower and higher dark matter density. And the mapped area is about 0.54 square degrees, about 2.5 times the size of the full moon on the sky. We're not talking about the whole universe. We're talking about a slice, a postage stamp on the sky, and even in that postage stamp, the universe contains enough galaxies to overwhelm the human mind. Here's a way to feel that number without flattening it. If you tried to look at just one galaxy per second, no breaks, no sleep, 800,000 galaxies would take over 9 days, just to glance. And yet the lensing analysis isn't a glance. It is careful measurement of subtle shape distortions across a massive sample, because the signal lives in the crowd, not the individual. This is why Webb's depth matters. More galaxies means more grass blades to read the wind. But then the universe offers a harsher truth. Mapping dark matter does not mean we have solved dark matter. A map is not an identity. It tells us where the influence is strongest, how it clumps, how it connects. It does not tell us what it is made of. It is like mapping coastlines without knowing what water is. And that's why this matters scientifically. A sharper map doesn't just look pretty, it becomes a stress test. It lets researchers compare the fine-scale distribution of mass against predictions, check how structures grew over time, and refine how galaxies form within dark matter halos. Reuters noted the map's usefulness for improving models of galaxy formation and the cosmic web structure, so the tension doesn't vanish, it deepens, because when you see the scaffolding more clearly, you notice details you couldn't notice before. You start asking questions that were previously impossible to ask. This is where the title of our journey becomes literal. Massive scale is not just about huge galaxies, it is about mass itself, where it sits, how it clumps, how it threads through space. The Webb dark matter map is a reminder that the universe isn't primarily a gallery of glowing objects. It's a gravitational architecture, an invisible construction that visible matter follows. NASA's own description says, ordinary matter tends to trace the same underlying structure shaped by dark matter. So when we talk about the early universe being massive, we are not talking about a mood. We are talking about a measurable landscape. Dense regions, connecting filaments and voids, already organizing the cosmos into a web. But then, the universe forces a more unsettling question. If the scaffolding is this real, this structured, this sharp, where does it lead when time moves forward? Because filaments are not the end, they are the roads gravity builds. And along those roads, matter doesn't just gather into galaxies. It gathers into something larger. Environments, overdensities, early cities under construction, so massive that even the hot gas between galaxies begins to glow in X-rays. So the next step in this story is unavoidable. If Webb can show us the scaffolding, can it also catch the moment when that scaffolding starts becoming a true gravitational metropolis? There is a moment when a scaffold stops being a scaffold, when the invisible threads of mass stop looking like a quiet pattern and start behaving like a place, a destination, a gravity-built city. And this is where the story becomes almost disturbing, because Webb and Chandra didn't just catch a cluster in the distant universe. They caught it while it was still pulling itself together, at a time when we expect the cosmos to still be learning how to build anything that big. A structure called JWST, a proto-cluster still forming, but already heavy enough to announce itself in 2 different languages. Webb sees the galaxies. Chandra sees the hot gas, the X-ray glow that only appears when gravity has become deep enough to heat in falling material to extreme temperatures. And when both agree, we're not just looking at a collection of lights, we're looking at a gravitational metropolis under construction. JWST is seen at about 1 billion years after the Big Bang, roughly 12.7 billion light-years away. Webb's images and analysis indicate at least 66 candidate galaxies in the structure, an overdensity so strong it stops feeling like chance. And then the number that makes the room go quiet. The protocluster's total mass is estimated at about 20 trillion suns. Trillion is a word the human mind can say without understanding. So let's translate it into something we can feel. If our solar system, our sun, our planets, every comet, every dust grain, were one unit. This structure is the mass of 20 trillion of those units, stacked into one growing gravitational basin. Not a single galaxy, an environment, a place where galaxies are beginning to behave like citizens rather than loners. But here's the strange part. Galaxies alone can lie to us. Because an overdensity on the sky can sometimes be a trick of projection, objects at different distances lining up like a coincidence. So the universe offered a harsher test. Chandra looked for what mature clusters often reveal, a huge cloud of hot gas glowing in X-rays. And in JD's ID1, Chandra detected that hot gas, evidence of a deep gravitational well and heating associated with cluster formation. That X-ray signal is not decoration, it's physics under stress. Gas falling inward, accelerated by gravity, shocked and heated until it reaches temperatures of millions of degrees, hot enough that it shines in X-rays. This is why the X-ray detection matters so much. It's a sign the protocluster has begun the violent transition toward a true cluster environment, what researchers describe as early phases of virial heating. In other words, this isn't just a crowd, it's a forming gravitational ecosystem. Picture this, it's nighttime, and you're flying over a landscape with the lights turned off. No street lamps, no headlights, no visible skyline. At first, it looks empty. But then you switch on a thermal camera, and suddenly you see the truth. A dense core of warmth, hot arteries branching outward, pockets of intense activity where something massive is gathering and compressing. That's what Chandra is doing here. Webb gives us the visible buildings, the galaxies. Chandra gives us the invisible heat signature, the gas that tells us the city is real, the gravity is deep, and the construction is underway. NASA and collaborators described the result as a surprisingly mature cluster environment for such an early epoch, but still emphasize it is a proto-cluster, meaning formation is in progress. That balance matters, because we're not claiming the system is finished. We're saying something more precise and more unsettling. Some properties typical of cluster environments are already present astonishingly early, including a halo of hot gas and an X-ray brightness peak. So the early universe starts to feel less like a quiet nursery and more like an engine room. Here is the problem stated cleanly. Galaxy clusters are among the largest gravitationally bound structures in the universe. The traditional expectation is not that they are impossible early, but that they should be rare, incomplete, still assembling, still messy. And JD's ID1 is exactly that, still forming, except its mass, 20 trillion suns, and its early hot gas signature put real pressure on how quickly large structures can assemble under standard cosmological assumptions. The Nature paper describes this detection at redshift about 5.7 and notes theoretical work suggesting proto-cluster shock heating typically begins at lower redshift, later times making this a rare early catch. We don't need to invent new physics here, we don't need to exaggerate. The fact-safe tension is enough. When we see a structure this massive, this early, with hot intracluster gas already present, the universe is telling us it learned to build big faster than our comfort zone. And if you were inside that protocluster, drifting between those young galaxies, you wouldn't feel a city, you wouldn't hear construction. Space would still be silent, but gravity would be everywhere. A slow, relentless pull shaping the motion of galaxies, guiding gas along invisible gradients, heating it as it falls. You would be inside a place that is becoming inevitable, and the only reason we can call it a place at all is because Webb and Chandra together can measure what your body cannot sense from afar, a concentration of galaxies and the hot gas that proves they share a common gravitational home. This is the shift. So far, the early universe could feel like a list of extreme objects, bright galaxies, early black holes, strange chemistry. But JWST forces a different realization. Webb isn't only catching isolated lights, it's catching structure, large-scale structure, the beginning of environments, regions where galaxies evolve together, collide, merge, compete for gas, and shape one another over cosmic time. And that means massive scale is not just brightness. It is mass distribution becoming architecture, a cosmic web node turning into a gravity city. But then the universe asks a larger question. If we can catch one city under construction 1 billion years after the Big Bang, how many are out there? How many rare overdensities are hiding in the sky, too spread out to find with a single deep pointing, too subtle to confirm without spectroscopy, too early to fit comfortably into our intuition? To answer that, we need something Webb cannot provide alone. We need breadth. We need a survey that maps enormous areas, looking for the network itself, so Webb can step in as the microscope that confirms what the wide field map suspects. And that's where the hunt widens from a single forming city to the cosmic network that connects them. Once we've seen a single city under construction, the question changes shape. It's no longer, can the early universe build something that big? It becomes, how many big things did it build, and how often? Because one discovery can be a miracle, but a pattern is a history, and patterns don't come from staring deeper into the same tiny patch of sky. They come from something Webb was never designed to be, a wide-field cartographer. That's where Euclid enters, not as a rival to Webb, but as its missing half. A mission built to scan the sky on a scale that feels almost unreal, using two core tools, weak lensing and galaxy clustering, measuring shapes and distances so the large-scale structure becomes measurable, not poetic. Euclid is built for breadth. Its wide survey is planned to cover at least 14,000 square degrees of sky, an area so large it stops feeling like an image and starts feeling like a census. And Euclid's core strength is statistical truth. Not the kind of truth that comes from one spectacular object. The kind that emerges when you measure millions of galaxies and ask, where are they dense? Where are they sparse? How do their shapes subtly shear under lensing? How does structure grow across time? It's a mission aimed at the geometry of the dark universe, mapping how cosmic structures evolve by measuring galaxy shapes and redshifts out to around redshift 2, roughly a 10 billion year look-back time. So Euclid doesn't try to out-stare Webb. It tries to out-scan the sky. Because when massive scale is the claim, the universe demands a cruel test. Are we seeing rare exceptions or the real distribution? And this is not vague. Euclid's data release planning is explicit. A major community release, Data Release 1, is scheduled for October 21st, 2026, with another quick release planned for June 24th, 2026. Multiple public-facing sources describe October 2026 as the first major cosmology data release, built from the survey accumulating wider coverage and deeper multipass observations in selected deep fields. Reuters framed it in a way that makes the scale feel immediate, a much larger release planned for October 2026, expanding the mapped sky by roughly 30 times compared with that early release snapshot. So this isn't just more images, it's the moment the map stops being a preview and becomes a framework wide enough to hunt the rare, the heavy, the statistically meaningful. Picture this, you're trying to understand a country. You can do it with a flashlight, walking street by street, peering into alleys, finding astonishing details. That's Webb. But if you want to understand where the cities are, where the population concentrates, where the roads converge, where the land rises and falls, you need a satellite map. That's Euclid. The flashlight reveals what a single building is made of. The satellite reveals where the cities even are, and the truly disturbing part is this. If we only use the flashlight, we can easily mistake luck for truth. We can fall in love with the brightest thing we happen to point at. But with the map, the universe can no longer hide its distribution. Here is the practical alliance. Euclid is built to find rare overdensities, lensing structures, and the statistical shape of the cosmic web across enormous area, because that's where you discover the unusual environments that almost never show up in a tiny deep field. But Euclid's breadth comes with a trade. In many cases, Euclid is telling us something is happening here. And then we still need to ask, what exactly is it? That's where Webb becomes essential. Webb provides the kind of confirmation Euclid cannot always deliver by itself: spectroscopy, physical diagnostics, and the kind of distant certainty that turns a candidate into a measurement you can defend. This is not a romantic partnership, it's an epistemological one. Euclid is the survey that finds the suspects. Webb is the interrogation room where the truth is forced into the light, line by line, break by break, diagnostic by diagnostic. And this is the deeper shift. Environment mapping is not just cataloguing galaxies, it's connecting galaxies to their neighborhoods. Because galaxies do not live in isolation. Their star formation, their mergers, their growth, and even their quenching are shaped by where they sit in the web, in dense nodes, along filaments, or out in the quieter outskirts. When we map environment, we stop telling stories about single objects and start telling stories about systems. A bright galaxy becomes more than a bright galaxy. It becomes a clue about the local density field, the dark matter scaffolding, the inflow of gas, the probability of companions, the history of interactions. This is the moment massive scale stops being a phrase. It becomes measurable as network behavior. But then the universe does what it always does. It complicates our confidence. Because wide-field surveys don't only confirm patterns, they expose the uncomfortable truths we tried to ignore. They expose cosmic variance, the fact that one tiny region of sky can be unusually empty or unusually dense, and we wouldn't know without context. They expose selection effects, what kinds of objects our methods favour, and what kinds they quietly miss. They expose how rare objects can distort our intuition. One astonishing detection can make us feel like the early universe was crowded. A wide survey can answer coldly, was it? Or did we simply point at the one place where the universe decided to show off? Euclid is designed to make that question unavoidable, and this is where we place you inside the real transformation, because you can see a beautiful image and still not know the universe. Knowing requires a harsh discipline. It requires a map large enough that the universe can't hide behind our choices. Euclid is not here to give us prettier pictures. It's here to reduce the freedom we have to fool ourselves, to turn the sky into a data set, wide enough that patterns become obligations. And then Webb arrives with the final act of honesty, confirming which candidates are real, diagnosing what they physically are, and forcing the story back onto measurable ground. So when we say networked universe, we're not being lyrical. We're describing a workflow, a map and a microscope working together. This is the calm answer Euclid and Webb offer together. Euclid maps the large-scale structure across enormous sky areas, using weak lensing and galaxy clustering as primary cosmological probes. Webb provides the deep physical follow-up where it matters most: spectroscopy, distances, diagnostics. And with the planned October 21st, 2026 data release 1, the map expands dramatically, moving from early snapshots toward a data set meant to support core cosmology analyses. This is how a network becomes measurable, not by a single breathtaking object, but by the ability to say, with statistical weight and spectroscopic confirmation, this is where the overdensities are. This is how the lensing field behaves. This is how galaxies change with environment. And then, inevitably, the story tightens around a question that sounds simple, until you realize how brutal it is. Because once we have a wide map, we can't hide behind anecdotes anymore. We can't ask, is one galaxy bright? We have to ask the real question: how many bright galaxies exist per volume? How common is the extraordinary? How crowded was the early universe really? When we stop relying on lucky pointings and start counting across the map. And once we begin that counting, the universe has a way of turning the numbers into something unsettling. There's a kind of discovery that feels safe. One distant galaxy appears, and we can treat it like a postcard, A single glittering exception, a cosmic accident, a beautiful, isolated miracle. But then we do the one thing scientists are trained to do when beauty appears. We count. Because the real shock is never one object. The real shock is the moment we realize the universe might be full of them. Not full in the emotional sense, full in the coldest sense we know, per volume. How many bright galaxies exist inside a slice of space at the same early time? How crowded was the newborn cosmos? That is the question behind the hype, and it's a question that can quietly fracture everything we thought we understood. Because if the bright ones are common, then the early universe wasn't a sparse wilderness. It was already a city grid. And this is where the story changes from look at that to how many. When we say the early universe was small, we usually don't mean its physical size. We mean something else. We mean it should have been empty, too young for many galaxies to shine like beacons, too early for a skyline. But astronomy is a discipline that punishes assumptions. A telescope can show us something astonishing, and the universe will ask only one question in return. Is it rare, or is it typical? Because if it's typical, then the scale changes, not metaphorically, statistically. A few rare objects can be explained away with luck. A whole population becomes a new reality. And Mumsy 14 forced that exact confrontation. In the MERM team's report, Mumsy 14 is not just far. It's remarkably luminous for its epoch, confirmed at a redshift of 14.44, only about 280 million years after the Big Bang. That's not just a record, that's a pressure test, because the brighter the galaxy, the more it pulls on the census. A bright-end object is like seeing a lighthouse on a coastline you believed was uninhabited. One lighthouse might be a fluke, but a lighthouse strongly suggests a shore, and a shore suggests a population. Here's the strange part. Counting galaxies is not like counting stars in a clear sky. It's like trying to estimate how many houses exist in a city by looking through a keyhole. Our keyhole is survey area. Our keyhole is a tiny patch of the sky, sliced into filters, stacked into exposures, and then interpreted through careful selection. The MOM team describes a survey spanning about 350 square arc minutes. That sounds abstract until we translate it into something our nervous system can feel. The full moon hanging over a city looks enormous to our eyes, but it only covers about half a degree across. In area, the moon is roughly 200 square arc minutes times 30. Not quite, it's about 700 square arc minutes in area. So 350 square arc minutes is roughly half the area of the full moon. Half a moon, that is the window. And inside that window, a galaxy appears at the edge of time, and it's bright enough to become a statistical weapon. Because the paper's implication is not simply, we found one. It's that the implied number density of bright sources at redshifts around 14 to 15 could be more than 100 times higher than pre-JWST consensus models expected. That is not a small disagreement. That is not a tweak. That is a difference that forces us to look at the early universe and ask a disturbing question. Were we underestimating how quickly light could gather into luminous systems? Or were we being fooled? Because there's always a second possibility, and astronomers are trained to fear it. Contamination, selection effects, false positives, objects that look like the early universe, but are actually closer imposters wearing the right colors. This is where the story cracks open, because at extreme distances the universe plays a brutal trick. It can make different things look the same. Truly ancient galaxy can vanish in some wavelengths and appear in others because its light is shifted, stretched by expansion until its spectrum drops sharply at the Lyman break. But other galaxies, much closer, can mimic parts of that behavior. Dust can redden. Old stars can change color. Different breaks in spectra can confuse. And if we accidentally count the imposters as ancient galaxies, we inflate the census. We build a city out of ghosts. So the bright end question lives or dies on one discipline, spectroscopy, not just imaging, not just it looks red. Spectroscopy is where the universe stops being an aesthetic object and becomes a measurable one. NASA has described how deep surveys like JD's use this method, first selecting candidates in images, then confirming them by finding the abrupt cutoff at the Lyman break and matching spectral features. That process is slow, it's careful, and it is the difference between a rumour and a result, because without spectroscopy, we can be seduced by shape and colour. With spectroscopy, we force the light to show its fingerprints. Imagine this. You're standing outside a massive apartment building at night. You can't see the people inside. You can't see the furniture. All you can see are windows. Some are dark, some are lit. Now here's the catch. Your vision is limited. You only get to look through a narrow slit in a fence. That slit is our survey area. If you see one bright window, you might think nothing of it. Maybe someone left a light on. But if you see bright windows again and again in multiple buildings, something changes. A pattern forms. Now the question becomes unavoidable. Is this building mostly empty or mostly occupied? That is what number density means in the early universe. Not just is there a galaxy, but how many galaxies are lit per block of cosmic volume. And because the early universe is supposed to be young, seeing too many bright windows becomes a contradiction, a mystery, a pressure wave. This is why survey area matters so much. Rare objects punish small searches. If we only stare at tiny regions of sky, we can be misled by cosmic luck, what astronomers call cosmic variance. Some regions are unusually rich, others unusually poor, simply because structure is clumpy. To measure populations, we need breadth, wide surveys that reduce the chance we're staring at an unusually lucky patch. That's one of the central promises of the next generation of mapping missions. ESA's Euclid mission, for example, is built to map the large-scale structure with a wide survey, covering at least 14,000 square degrees, more than 1/3 of the sky, specifically avoiding crowded planes where confusion is high. And when Reuters covered Euclid's early data release, it emphasized the logic. Even the first release was only a tiny fraction of the final atlas, with a much larger release planned for October 2026. That scale is how we stop arguing about luck. That scale is how we turn one miracle into a measured population. But here's the problem. Wide surveys find candidates. They find patterns. They find overdensities. They suggest the network. Yet the early universe is a ruthless place for lookalikes. So the second half of the machine has to exist too. A spectroscopic instrument that can confirm distances, not as vibes, not as aesthetics, but as defended measurements. That is where Webb remains the final judge. It's not just that Webb can see faint light, it can verify what that light is. And that verification stabilizes the census. We stop counting ghosts, we start counting galaxies. Now, the bright end story doesn't only live at redshift 14, because once we begin counting, the universe reveals something else. Not just that early galaxies can be luminous, but that later, in a different era, some galaxies can become massive and quiet in places where they should be alive. A JWST study describes a galaxy they call the red potato, observed and discussed at a redshift around 3.25, a time when the universe is far older than the cosmic dawn, but still early enough that growth should be intense. The striking detail is not just its nickname, it's the paradox in the paper's framing. A massive, quiescent galaxy, about 110 billion suns worth of stars, sitting in a gas-rich environment associated with a cosmic web node or protocluster region, yet showing suppressed star formation. This is not the same kind of shock as MUMZ-14. MUMZ-14 challenges how quickly light can appear. The red potato challenges something more psychological. How can a galaxy sit near fuel and choose silence? And the reason it belongs in this part of our journey is simple. It reminds us that massive is not a single property. Massive can mean bright. Massive can mean heavy with stars. Massive can mean embedded in a dense environment. And when we count populations across time, we begin to see the early universe not as a clean timeline, but as a landscape full of contradictions. Some places light up too fast. Some places go dark too early. And those contradictions are not failures. They are the data. And now, hold this in your mind for a moment. You're not looking at a single galaxy anymore. You're looking at a census that suggests the early universe may have been more crowded with luminous systems than we expected, enough that one confirmed object can ripple outward into model tension. That feeling is unsettling for a reason, because it changes our inner picture of cosmic history. We like to imagine the beginning as quiet, empty, a slow dawn. But if bright galaxies are common earlier than expected, then dawn starts to look less like a sunrise and more like a city switching on. And once we see that, the word scale stops meaning distance alone. It becomes a measure of population, density, network, how quickly structure becomes inhabited by light. So yes, we can confirm a galaxy at the edge. Yes, we can defend its distance. Yes, we can argue about models. But the deeper question remains, and it refuses to be quiet. If the early universe contains more bright galaxies per volume than our pre-Webb expectations, then what exactly is doing the heavy lifting? Is it the physics of star formation ramping faster than we thought? Is it the way galaxies assemble in the densest regions? Is it something about the environments, the scaffolding, that makes some regions ignite early and often? Because this is the unavoidable truth about counting. When the numbers don't match the story, we don't get to keep the story. We have to follow the numbers. And the numbers are pointing toward a universe that very early on may have been far less empty than we were prepared to admit. There are mysteries that announce themselves with fireworks, and then there are mysteries that arrive like a draft under a closed door, so soft you almost doubt it's real, until you feel the temperature change. This one hides inside a single, calm phrase. How fast is the universe expanding right now? It sounds like a technical detail, but it isn't, because the answer is not just a number. It is a verdict on our entire cosmic story. How quickly space stretched, how easily matter gathered, how early the first structures could tighten their grip. And right now, we have two answers. Both are measured with real instruments. Both are defended by serious teams. Both are repeated across years of work. And they do not agree. That's when the real problem appeared. The James Webb Space Telescope was never meant to solve this tension with a single heroic observation. Webb's role is colder than that, more disciplined. Webb was designed to check whether our most trusted local measurement is being subtly fooled by crowding, by blending, by the cruel fact that the distant universe is visually messy, because the local method, often called the distance ladder, depends on using Cepheid variable stars as a kind of living ruler. Cepheids brighten and dim with a rhythm that lets astronomers infer their true brightness. And if we know how bright something truly is, and how dim it looks, distance stops being a guess. But there's a danger here. A Cepheid doesn't live in a clean, empty lab. It lives inside a galaxy, inside clutter, inside light that does not belong to it. And if that extra light leaks into our measurement, the Cepheid looks brighter than it really is, which makes the galaxy look closer than it really is, which makes the expansion rate look faster than it really is. That's the nightmare scenario. Not new physics, just a subtle, human kind of error. Too much light in the same pixel. So Webb went hunting for a very specific suspect, crowding and blending. And Webb did it the only way that matters. By looking at the same galaxies with sharper eyes. Imagine this. We're standing on a distant street at night, looking up at an apartment building. We're trying to measure the brightness of one single candle. One window, one tiny flicker. That candle is our Cepheid. But in the window next to it, There's a lamp, and behind the curtain, a television glow, and in the hallway, a light spilling through a cracked door. From far away, all those lights blur together, and suddenly that one candle looks stronger than it truly is. Now here's the difference. Hubble can see the building, Webb can separate the windows, Webb can test whether we've been accidentally measuring the whole apartment, while calling it a candle. That's the point of this chapter. Not drama, verification. In 2025, a Webb-led approach pushed that verification into an almost uncomfortable purity. Researchers focused on what has been described as a perfect host setup, choosing a situation designed to reduce confusion from background light, so the Cepheid measurements could be tested under cleaner conditions. The point wasn't to chase headlines, the point was to remove excuses. If the tension were just a mirage created by crowded star fields, then Webb, under these cleaner conditions, should see the illusion collapse. But that collapse did not arrive. The result reported no evidence that this kind of crowding/blending bias could explain the full discrepancy, and it found an expansion rate consistent with the local distance ladder direction rather than fixing it downward into perfect agreement. That is a very specific kind of terror, because it means the tension is not easily dismissed as sloppy measurement. It means the universe is either doing something strange, or we are missing something essential about how the universe evolved. Let's say the numbers plainly, because hiding them makes the mystery feel softer than it is. Under the standard model used to interpret early universe signals like the cosmic microwave background, the expansion rate is expected around 67 to 68 kilometers per second per megaparsec. But measurements using Cepheids and supernova host galaxies, checked with Webb and Hubble, land closer to about 73 kilometers per second per megaparsec, with studies describing the mismatch on the order of several percent. A megaparsec is about 3.26 million light-years, a distance so large it's almost rude to our intuition. So translate it into something we can feel. This number is a statement about how much extra space appears between galaxies every second, across spans of millions of light-years. Even a few percent difference isn't a rounding error, it's a different universe. And what makes this disturbing is that Webb's job was to expose a measurement flaw, and instead, it helped. Remove one of the easiest escape routes. This is where we have to be honest with ourselves. We like the idea that cosmology is settled, that Einstein and the equations and the satellites have already written the final script. But this tension keeps doing something humiliating. It forces us to admit that precision can deepen confusion. And if you really let it sink in, you realize the expansion rate is not a detail sitting at the edge of astronomy. It sits in the center of the early universe story, because the expansion history controls how fast matter can assemble into the first dense structures. If the universe expands a little differently than we think, earlier, later, smoother, rougher, then every timeline we tell about structure growth has to be rechecked with colder eyes. This is why the chapter belongs here. Because massive scale is not just about what Webb sees, it's about whether the stage itself, space-time, has been measured correctly. You will hear people say the words, new physics. And yes, there are proposed ideas that try to bridge the gap, involving dark energy behavior, additional components, or changes in how gravity behaves under certain conditions. But none of that is confirmed, and we have to stay loyal to what is measured. So the fact-safe statement is simple. The mismatch persists, and its interpretation remains an active research area. Webb did not arrive like a judge delivering a verdict. It arrived like a forensic scientist. It checked the fingerprints, it remeasured the scene, and the scene still refuses to align with our expectations. Here's the strange part. When we hear massive scale, our minds jump to images, galaxies, black holes, clusters. But scale is also statistical, environmental, structural. It lives in the relationship between expansion and assembly, between the stretching of space and the ability of gravity to build anything inside it. So Webb's cross-check matters because it guards the foundation. If the foundation is slightly wrong, then every measurement built on top of it, distances, ages, growth rates, has to be handled with more humility than we prefer. And yet, the most unsettling part is not that we don't have an answer. It's that the universe has given us two answers that both look real, two answers that pass serious tests, two answers that force us to keep going, not with hype, but with discipline. Because the tension is not an embarrassment, it's a clue, and the clue is telling us something simple and difficult. We are measuring the universe at a depth where even small disagreements can rewrite the shape of the entire story. If Webb can confirm that the local ladder is not easily fooled, and the early universe inference still points somewhere else, then the uncomfortable question becomes unavoidable. What changed between the young universe and the one we live in now, that our best model still doesn't fully capture? And if that change exists, then every map of massive early scale has to be read with new eyes, because the stage may be shifting under the actors. There's a particular kind of silence that arrives when the universe stops being a picture and becomes a measurement, not a poetic measurement, a brutal one, a wavelength, a line, a break, a tiny signature that refuses to lie. Because for most of human history, the early universe was not a place we could verify. It was a story we told ourselves with fragile evidence, blurred light, hopeful colors, statistics balanced on thin assumptions. But now, in the middle of the 2020s, we are watching the early cosmos harden into something colder and more definite. Not because it suddenly became larger, because we finally learned how to count it. And this is where the meaning of massive changes. Massive is not a metaphor for wonder. It's not a thumbnail saying the universe was crazy or insane. Massive means the early universe already contained confirmed extreme distance galaxies, abundant black hole growth, chemical complexity, patches of transparency inside a hydrogen fog, maps of invisible matter, and even city-scale environments where galaxies were gathering together, all anchored in observations that can be checked and challenged. So, we don't need to exaggerate. We just need to look at what the measurements actually say and let the scale do the emotional work. Because the scale is disturbing enough on its own. When we say the early universe was massive, we're not talking about the universe being physically bigger back then. In fact, the early universe was denser, hotter, tighter, compressed into a younger geometry. What's massive is something more unsettling. How much was already happening across how much space so early? Massive means massive in populations, not just one shocking object, but enough objects to force a census. Massive in mass distribution, dark matter shaping structure before starlight fills it. Massive in connected environments, not isolated galaxies, but neighborhoods and proto-cities. That's why serious coverage keeps returning to the same uncomfortable pivot. It's not one bright galaxy that matters. It's what the existence of these objects implies about how crowded the early universe may have been. And this is where our calm answer begins. When NASA confirmed MOMSI 14 at redshift 14.44, they weren't just adding another point to a chart. They were moving the edge of confirmed reality outward. A redshift that high means the light left, when the universe was only a few 100 million years old, so early that Earth didn't exist, the Sun didn't exist, and even the Milky Way was still an unrecognizable idea. We can say that number, 14.44, in a calm voice, but we should feel what it means. It means the early universe is no longer a blank prologue. It is a populated place, and once an object is spectroscopically confirmed at that edge, it becomes a calibration point for everything else. We think we know about how many bright objects should exist that early. One object is startling, but one confirmed object at the edge is also a question that spreads outward like a stain. If one exists, How many more are hiding just beneath our detection limits? For a while, little red dots sounded like a visual curiosity. Small, red, everywhere in Webb's deep fields. But then the interpretation hardened into something far heavier. Evidence consistent with young supermassive black holes embedded in dense ionized gas cocoons that reprocess the light, making these objects look redder than a simple galaxy would. This matters because black holes are not decorative. They are engines. They don't just sit inside galaxies. They can dominate how gas behaves, how it heats, how it flows, how it collapses, how it survives. And one of the stabilizing corrections reported in popular coverage is also psychologically important. Estimates for the black hole masses in these systems can be far lower than some earlier, more alarming interpretations, reducing the sensation that we'd discovered impossibly huge monsters too early. That doesn't make the early universe gentle, it makes it busier, because the most unsettling implication is not one impossible black hole. It's the hint that this phase, rapid growth inside a cocoon, may have been common, not rare. And if early black hole growth was common, then the early universe wasn't just forming galaxies, it was forming power sources, quietly, repeatedly, everywhere we look deep enough. There is another kind of evidence, sharper, more diagnostic, when a galaxy's spectrum carries the signature of an active nucleus. GNZ11 at redshift 10.6 became famous as one of the earliest known galaxies, but Webb's spectroscopy pushed the story into a more uncomfortable register, emission features consistent with an accreting central black hole. This is where we have to be careful with language. We don't need to claim cosmic dominance like a headline. We only need to accept what the data style implies, components in the spectrum that match the kinds of transitions astronomers use to diagnose an active nucleus. And then we let the consequence speak. If an accreting black hole is already present in a luminous galaxy at that time, then black holes are not late-game characters. They are part of the early universe's infrastructure, woven into the same era that gave us the first bright galaxies we can confirm. And this creates a bigger problem. Not a poetic one, but a modelling one, because early accreting black holes exist. But the question of how the first seeds formed and grew remains an active research area, open, constrained, argued over, not resolved by a single telescope. We are not forced into fantasy, we are forced into patience. Now we move from objects to the space between them, because the early universe wasn't just a collection of islands, it was an environment. And early on, that environment was hostile to certain kinds of light. Neutral hydrogen acts like a fog, absorbing specific photons, especially those around Lyman alpha, making the universe less transparent in that era. So, when observers report Lyman alpha detected at redshift 13, it is not just a line on a plot. It is a hole punched through the fog, and the safe implication is precise. This does not mean the entire universe was already reionized. It means at least some regions, locally, allowed transmission earlier than many expectations. This is where the universe becomes cinematic in the most literal sense. Not because we are making it dramatic, but because we are watching the first regions of transparency appear like openings in a storm cloud. Imagine you're standing in a long hallway filled with thick fog. You can't see the far door. You can't even be sure it's there. Then someone turns on a small light at the far end. You still don't see the whole hallway, but you see a faint pinprick, because around that light the fog has thinned locally. That's what a Lyman alpha detection at these redshifts feels like. A small region telling us the environment is changing, even while the larger volume may still be opaque. And that matters for scale, because reionization is not a single moment. It is a volume-wide process, patchy, environmental, linked to where galaxies are and how they shape the space around them. We also have a colder kind of proof. Chemical lines. Oxygen is not a mood. Nitrogen is not a vibe. These elements appear through wavelength-locked evidence that either matches or it doesn't. And reports tied to ALMA observations have described oxygen detected in the galaxy JWST 14-0, demonstrating chemical enrichment at extreme redshift. This matters because oxygen requires a chain of events. Stars must form. They must live. They must process lighter elements into heavier ones. And then that enriched material has to be present in a form we can detect. So this isn't saying early galaxies were mature like today. It's saying something more precise and more unsettling. Star formation and chemical processing happened quickly enough to leave detectable fingerprints extremely early. And when we place that beside reports of unusual nitrogen features in other extreme redshift systems, the emotional picture becomes heavier. The early universe wasn't merely producing stars, it was already producing variety, it was already producing complexity. Not as a rare accident, but across multiple systems we can now study. Now we go deeper than light. Because if we want the true meaning of massive scale, we have to talk about what dominates the universe's structure while remaining invisible to our eyes: dark matter. Galaxies are not the beginning. Mass concentrations come first, and galaxies later ignite inside them, like lanterns hung on a frame you couldn't see. And in 2026-era reporting from NASA's Jet Propulsion Laboratory, Webb data has been used in gravitational lensing work to produce extremely detailed dark matter reconstructions, leveraging the distortions of huge numbers of background galaxies. Here's the strange part. This isn't a pretty visualization. It's a measurement of how space itself is bent by mass. Webb's resolution and depth matter because they increase the number of usable background galaxies and sharpen the reconstruction compared with older maps. And once we can reconstruct mass distribution with this kind of detail, we can speak more concretely about the cosmic web, its concentrations, its filaments, its threads. Not as mythology, as a derived field from lensing data. And this is the clearest correction to the way our minds want to picture the early universe. We imagine a few isolated points of light, but the universe is a network, a scaffold, a structure in progress, and that structure is what massive really means. Then the story becomes even more human, because the scale starts resembling something we recognize: environments, neighborhoods, crowds. A protocluster like James Webb D1 is described as an early large-scale structure, around 1 billion years after the Big Bang, with enormous total mass and many candidate galaxies, an early city in the making. And the clincher detail reported in connection with the system is the detection of hot intracluster gas in X-rays by Chandra, a sign of a deep gravitational potential well. This is not a poetic statement. Hot X-ray gas is physical. It's matter heated by gravity inside a massive environment. So Webb is not only showing us early galaxies, it's catching early large-scale structure, gravity building big places early enough that we have to take the timeline seriously. And this creates pressure, fact-safe pressure, because assembling massive structures early under standard assumptions is not a casual detail. It becomes a question of how quickly the universe can organize matter into these environments. And then, to measure a network, we need two different ways of seeing. We need breadth and depth. That's where ESA's Euclid becomes part of the same story. Wide-field imaging and statistical mapping of large-scale structure across huge areas of sky. And there is a schedule reality here. A much larger Euclid release is planned for October 2026, expanding mapped sky dramatically. Euclid finds patterns, rare overdensities, lensing structures, the places where the cosmic web thickens. And Webb does what Webb does best. It confirms distances. It diagnoses physics. It turns candidates into defended measurements. That's how environment mapping becomes real. Connecting galaxy properties to their neighborhoods requires both the map and the microscope. And once we have that, massive stops being a feeling. It becomes cartography. Now we touch the final layer, one that doesn't live inside any single galaxy. the expansion history. Webb's role here is not to declare victory, it's to test a specific vulnerability in the local distance ladder, where the measurements of Cepheid stars used to calibrate distances could be biased by crowding and blending. ESA has described Webb and Hubble work that affirms the universe's expansion rate measurements in a way that emphasizes this blending issue, exactly the kind of systematic effect that must be tested if we're going to trust our numbers. And the perfect host approach, targeting a clean environment to reduce background contamination, has been discussed in connection with confirming no significant bias in those Hubble constant measurements. So the fact-safe statement remains calm. The mismatch between late universe distance ladder values and early universe CMB inferred values has not simply evaporated. Interpretations exist. Proposals exist. But none are confirmed in the way a spectral line is confirmed. So we stay with what is measured and accept what that implies. The early universe story isn't only what formed. It's the expansion history that shaped how structure could grow at all. Now, with all of this held together, we can finally say the calm answer without hype. Webb has revealed the massive scale of the early universe, not by making the universe bigger, but by showing us the early universe was already organized, already populated, already energetic, already chemically active, already environmental, already a place where mass was shaping scaffolds, where gas was igniting into stars, where black holes were feeding, where hydrogen was slowly losing its grip on light. And this is the moment we should allow ourselves a single direct human confrontation. Because the numbers are not just numbers. They are time, they are distance, they are reality arriving late. And here's the moment for you. You are sitting in a present-day room, surrounded by modern noise, electricity, screens, clocks. But the photons that Webb studies left their galaxies so long ago, those photons travelled for more than 13 billion years, through expanding space, through gravity, through fog, through emptiness, and they arrive as something we can test. Lines, breaks, counts, not myths, measurements. And that's why the ending is not mystical. It's almost painfully grounded. The early universe wasn't empty. It was already organizing. Matter into scaffolds, gas into stars, gravity into cities. And the human part is not that we are special. The human part is that we are small. But we are a species that learned to turn faint infrared light into a truthful map, quietly expanding the size of our understanding, without having to exaggerate a single word. So we end on a quiet truth. We didn't make the universe more dramatic. We just made it harder for the universe to hide. And in that new honesty, the early cosmos does not look like a simple beginning. It looks like a vast construction site, already alive with structure, already heavy with consequence. And we are still only reading the first few lines.